Hello, hello, hello. Welcome, everybody. Please feel free to say hi in the chat. Nice to have everybody here. How's everybody doing? Welcome to our GCSE chemistry web class on alkanes. If you've been to our sessions before, hopefully you'll know how this works. But if you haven't, then lovely to have you. Welcome. If you wanted to make sure you've downloaded today's slides, the link's in the description. Hi, Maya. How you doing? If you are a regular student, welcome back. Nice to have you. If this is your first time, then please feel free to ask as many questions as you can. The more you ask, the more you'll get out of these sessions. So yeah, hopefully we'll manage to get through everything that we've got planned and we can answer all of your questions and cover this GCSE topic perfectly. But hi Samaya as well. Lovely to have you guys back. I've done ages, and I think that's probably because we haven't had a chemistry class in ages. Hopefully everyone can hear me and see me okay. Again, feel free to say hi in the chat if you're here. We'll get started in about a minute. We'll just give everyone a chance to have a go at getting themselves online, getting their slides downloaded. About these slides, if you haven't already worked it out, is that you can save them, you can scribble on them now if you want to, or if you want to keep it, just listen, make some notes separately, you can reuse our slides again at a later date for revision. Hopefully this is going to be a bit of a revision class anyway, but you can always use this again as a revision class, you know, with the YouTube video, because the YouTube video will stay on our account. So you could, in a couple of weeks' time, have a look back over everything, write out all of your notes again, use the notes from this revision class. So really, really useful. So if you haven't already got them, get them downloaded. So this week's or this month's GCSE YouTube class is on alkanes. Alkanes are a homologous series, a type of chemical. So we're going to look at what you need to know for GCSE. Oh, hi, Faber. Lovely to have you. Welcome. Nice to have you here. So I think we should probably get started. So just a little bit about me. I'm the lead chemistry teacher at SnapRevise. I've got a PGC in chemistry education in science, but chemistry being my specialism because it's my favourite. And I've been teaching A-level chemistry for over 7 years now, so ages. Oh, hi, Letitia. Lovely to have you here as well. Hopefully I said your name right. Apologies if I didn't. So our objectives for this session, we're going to hopefully understand the definitions of common terms used in organic chemistry. We're going to understand what an alkane is. What do we mean when we say an alkane, including examples. And we're going to understand the trends in the physical properties of alkanes as well. So we'll remind ourselves what physical properties are, and then we'll look at the trends or the patterns in those as well. Oh, brilliant. Thank you for letting me know. Okay, cool. So the three main exam boards, we've just showing you what it is that your exam board is expecting from you. So for AQA, the specification points that we're expecting you guys to, that they are expecting you guys to be able to know, talk about, describe, etc. are these ones here. For OCR, this is the ones that we're going to be using from your specification, that we're going to be covering, sorry. And then Edexcel, these are from you. Now, a lot of GCSE content is very, very similar in all of the exam boards. So there's not a huge amount of differences. If there are major differences, then I will point them out. But like I said, GCSE, the content is very, very similar across all three of the main exam boards. Feel free to refer back to those, to these specification points if there's something you're unsure about, if you don't know how much you need to know, how much detail. The specification is an amazing resource that students forget to use. So definitely use it. Hi, Dominic. Lovely to have you. Welcome. Okay, so let's work out what we already know. If you can, try and give me as many answers as possible. I'll give you a little bit of a chance to type stuff in the chat if you can. If you can't, don't worry, doesn't matter. I will give you the answers and we'll write it down together. But like I say, the more you put in, the more you'll get out of these sessions. So have a go. It doesn't matter if you get it wrong. I don't care. And we're on the other side of the internet anyway, so no one else will care either. Okay. So, oh, disappeared. I'm back again. Don't know what happened there. What is crude oil? Good, yeah, lovely. So crude oil is made of hydrogen and carbon molecules, or hydrocarbon molecules. Brilliant. Crude oil is a mixture of hydrocarbons. Oops. Hydrocarbons, which are brilliant. Well done, Dominic. Crude oil is a mixture of hydrocarbons. It's mostly alkanes. So it's mostly made of alkanes, which we're going to look at in this session today. Oops, alkanes plural. Some alkenes, which we're not going to cover today, and also some hydrogen as well. It looks like we've already, oh, hi Rhea, lovely to have you here. I've also got some example, sorry, it looks like we've already got somebody who's given us an example of what a hydrocarbon is. Anybody want to tell me what is the key word, if you know, what's the key word that the examiners are going to be looking for when you give a definition of a hydrocarbon? There's 3 words, which is the absolute minimum that you can say when you answer an exam question defining a hydrocarbon. There's a minimum of 3 words. Well done, Maya. Only people forget to say. So hydrogen and carbon only. So really, really key word. They want to see that you've written the word hydrogen, they want to see you've written the word carbon, and they want to see you've written the word only. If you don't say only or something to that effect, that there's very definite, hi Zara, lovely to have you back. That's very definitely saying that there are only hydrogen and carbon atoms, or if you can say contains hydrogen and carbon atoms and nothing else if you wanted, but the key point is if you haven't mentioned that there is nothing else in there, that it is only hydrogen or carbon, they won't give you the mark, which is a bit mean, but that is the definition. So hydrocarbons, they are what we call simple molecules, so nothing too complex. You don't have to put that for the definition, so I'm going to put it in brackets, but we do have to say they contain only, I'm going to put that in capital letters and underline it. It is only, contain only hydrogen and carbon. So you can just say they contain only hydrogen and carbon, or we can say they contain only hydrogen and carbon atoms. That is also fine. Lovely. Yeah, I've missed them as well, to be fair. Hello, hi Shreya as well, lovely to have you here, welcome. So Dominic does a great question. It's a haloalkane, a hydrocarbon. Very good question. Now, if I say to you, do you know which group the halogens are? Do you know which group the halogens are? Or what a halogen is? Because a halogen is a halogenoalkane. Yes, well done, group 7, fantastic. So a halogenoalkane is a type of compound that contains group 7. So a halogenoalkane, as in or a haloalkane is the shortened version, is an alkane with a halogen on it. So to answer your own question, Dominic, and anybody else, is a halogenoalkane a hydrocarbon? Does it contain only hydrogen and carbon atoms? Do we reckon? So it's an alkane with a halogen on it. So no, good, well done. It's not a hydrocarbon because it also has a halogen on it. So just alkanes, not haloalkanes or halocarbons. Great question though. Okie dokie. So let's have a look at what these alkanes are then. So if we're thinking in terms of our organic chemistry, what is organic chemistry? It's a description of what? Does anybody know? We talk about organic chemistry as a part of chemistry. You can have physical chemistry, you can have organic chemistry, and it's actually the study of simple carbon-based molecules. So yeah, brilliant, Shreya, well done, exactly. Fantastic, Dominic, brilliant, perfect. So organic chemistry is the study of simple carbon-based chemistry, anything containing carbon, simple carbon-based molecules. Lovely, cool. Do we know what a functional group is? This is a word that we use quite a lot at A level, but we don't tend to use very much at GCSE. And it does get used every now and again, but we don't really study what it means. What is a functional group? If I talk about a functional group, what do we think it is? If you're not sure, have a think about what those words mean. A group that is functional, a functional group. So if I'm talking about a functional group on a molecule or on a substance, what is that? What do I mean by functional group? Yes, Dominic, really nice. Well done. Yeah, it is. That's a lovely way of putting it. So it's the atoms in a molecule which are responsible for its reactions, which are responsible for how it behaves chemically. Yeah, Letitia, brilliant. Causes the characteristics of molecules. Yeah, lovely. So a functional group is the atom or atoms, can be more than one. It often is more than one, but it can also just be a single molecule, single atom, sorry, in a molecule that are responsible for the no, actually, let's say responsible for the molecules' chemical reactions. So often, especially with things like alkanes, so coming back to our example of a haloalkane, a halogenoalkane, in a halogenoalkane, which isn't a hydrocarbon, but is a type of molecule, it's the halogen that's the functional group. The rest of the molecule, the alkane bit, doesn't really do anything in a halogenoalkane. So the functional group is the atoms in the molecule that are responsible. Oh, that might help if I wrote probably responsible for the molecule's chemical reactions. If at any point you can't read my handwriting, guys, please let me know, because I'll try and rewrite it. I do try and say what I'm writing as I write it and repeat it, but if you can't read what I've put, then just let me know and I can rewrite it. Okay, the general formula then. A general formula. We need to know general formulas. We need to know general formulas of alkanes, alkenes, and alcohols at GCSE. Those three things. If you're doing further, I think it's also carboxylic acids as well. So we need to know our general formulas. Yeah, it would, Samaya, exactly right. Exactly right. So the general formula, if we're talking about like a general equation or a general practice, we're talking about how something that can represent anything of that practice or of that whatever it is that we're describing. So in this case, our general formula is the formula that we can use to describe all molecules in a type of substance. So for example, who was it? Yeah, lovely. Well done, Dominic, exactly. Well done, Letitia. And Lahey Saint as well. Brilliant. So we can use a general formula to describe any molecule of an alkane. And you're exactly right. For our alkanes, it's CnH2n+2, which I think we're going to write down later. But general formulas in general describe the proportions of different chemicals, different atoms in a chemical for all of the molecules in that group. So a general formula is the proportions of my pen takes a while sometimes and I can't see what I've written. The proportion of different atoms of each element in the molecules of an homologous series. Homologous series. And we're going to look at what that word means in a second. That's supposed to say series. So we're going to look at what this word homologous series means in a second. Okay, if anybody's not happy about any of those, let me know. You don't have to be able to describe any of these at GCSE, which is good. You do at A level, but not at GCSE, which is lovely. What we do need to be able to describe at GCSE, though, is what makes a homologous series. So a homologous series is a family of organic molecules. And as I mentioned earlier, Samaya, no, great question. I think I've just answered it. So no, that previous slide, you wouldn't be asked to repeat the definitions of. You would be asked to do the definition of a hydrocarbon, which we did a few slides ago, but not this one, not those ones on the previous slide. So yeah, no worries. Good, lovely. They've got the same general formula. Does anybody else know what makes a homologous series? The family of molecules, the molecules present, have the same general formula in a homologous series. They also, really nice, Dominic, fabulous. They have the same functional group, which we've just looked at what that means. That's not nice. Oh, sorry, Siri was telling me off for speaking. The same functional group. What they all just say, yeah, lovely. They react in the same way, so similar. So they might not be absolutely identical, but they will be very similar chemically. So they have similar chemical properties. So chemical properties, just a reminder, compared to physical properties, chemical properties are how they react chemically. So they have very similar chemical properties, as in they react very similarly. Yeah, good, Letitia, well done. Love the point from Dominic about the differing by CH2. That's something that we often forget, and it's quite hard to get your head around. So I think it's useful to draw pictures if you're not sure, which we'll come to in a minute. But each different member of the family differs by CH2, one carbon and its two attached hydrogen atoms. So I'm going to call them neighboring molecules. And what I mean by that is, if you've got we've got 3 carbons, for example, then the one with 4 carbons will have an extra carbon and 2 hydrogens, and the one with 2 carbons will have 1 fewer carbon and 2 hydrogens. So neighboring molecules, as in ones that are next to each other in the family, differ by CH2, big C, big H, little 2 down the bottom, in their molecular formula. And we'll look at this in a little bit more detail in a few slides' time. And finally, any ideas what, I don't think anyone said it yet, what happens with their physical properties? So they've got very similar chemical properties because the functional group is identical. So they're all going to react chemically in the same way or very similar way. But with their physical properties, so things like boiling point, melting point, density, molecular mass, viscosity, all of these things, their physical properties, what kind of trend do we see? Are they all the same? Are they all completely different? Do they follow a pattern? Anybody got any ideas? If we're making the chain longer every time, do you think we're going to have the same physical properties, or do you think they're going to change? Yeah, well done. Well done, Shreya, exactly right. As the molecules become bigger, the properties change with the molecules. So they follow a gradual trend or a pattern, we can call it. So there is a gradual trend or a gradual change, or yeah, good, or a gradual variation in their physical properties. Now, we don't have to know any more detail than that at GCSE, thank goodness. You just have to know that there is a gradual trend. You don't have to be able to describe the gradual trend. So that's good. Okay, lovely. Let's keep going. If anyone has any questions at any point, please just pop it in the chat. And we will try to come to them. We're probably not going to be able to cover everything in this web class today because this is a big web class, but we'll do our best. Yeah, Letitia, exactly. Lovely. Examples of homologous series in everyday life are like alkanes. So we use methane quite regularly, and that's why our picture, if you wanted to scroll back to the beginning of our PowerPoint, there's a picture of a cow doing a bit of a fart, because farts and burps of cattle, animals, sheep, cows, etc., release a lot of methane into the atmosphere. So methane is one of the members of a homologous series, the alkanes. So that's an example. Alkenes, which is another homologous series, we use lots when we're making plastics. They're a big, what we call feedstock, a starter chemical for making plastics. So really, really useful compounds. Okay, so alkanes are a homologous series, we've just said. So the structure of an alkane, absolute pleasure. The structure of an alkane are hydrocarbons. We know that alkanes are hydrocarbons. So an alkane, the ane bit, the key thing about the ane bit is that they contain only carbon-carbon single bonds. They contain only single bonds between carbon atoms. This is different to alkenes. Alkenes contain double bonds. So I'm going to put that up here just so that you know why we've put this. The alkene homologous series alkenes have carbon-carbon double bonds. Alkanes have carbon-carbon single bonds, just like this one down in the bottom right-hand corner. So the way we differentiate between an alkane and an alkene with the double E has a double bond. An alkane with the single E has a single bond. And the other way we can describe this is with this word saturated. You may have heard of unsaturated fats or saturated fats when you're talking about, margarine and butter and things like that. And that's what this word means. It means if it's saturated, it means it contains only single bonds between carbon atoms. So if you're ever in the supermarket and you see something saying it's got lots of saturated fats in it, you can say, oh, I know what that means. The general formula for alkanes, lots of you have said already, which is brilliant, is CnH2n plus 2. So you've got twice as many hydrogens as you do carbons, plus 2 on the end. So you must remember to put the 2 on the end because alkanes have got the extra 2. Alkenes don't, they are different. So if we substitute N into the general formula, it gives us the molecular formula. Molecular. Alkane. So for example, if we wanted to know methane with 1 carbon, we put a 1 where the N is. So you have C1H, 2 times 1 plus 2. So 2 times 1 is 2, plus 2 is 4. So C1H4 or just CH4. And that is the molecular formula for methane. We're going to write these in a second. Alkane, lovely. Okay, if anyone has any questions, don't forget to ask. So when we come to naming alkanes, I've already mentioned that if you have 1 carbon atom, we call it methane. So it's meth. The alkyl group is called meth. Alkyl means the carbon group. So the first part is the alkyl group. So if you've got 1 carbon, you call it meth something. Lovely, Deeksha. I was just about to ask, if you've got 2 carbons, what do we call it? Ethane. So that's eth, meth, eth. What about 3? Does anyone know 3? The second part is our ane, which you guys have already said, which is brilliant. And that tells us the homologous series or functional group. Tells us that it's an alkane. Good. Prop. Well done, those of you that got propane. Propane is an alkane with 3 carbons. Is propane. And the final one? 4. What's 4? Anyone know? Lovely. Bute. Very nice. And just as a quick way of remembering it, because you do need to know how to name something with 1, 2, 3, or 4 carbons. So just a quick way of remembering it, I've always said mice eat peanut butter. Or lots of people say many elephants prefer butter. Or monkeys eat perfect bananas. Things like that. If you want to come up with a phrase, I've always used mice eat peanut butter, and then I just picture a mice that's scooping peanut butter out the jar. To help me remember, MEPB. M for 1 carbon, meth for 1 carbon, eth for 2 carbons, prop for 3 carbons, and bute for 4 carbons. So if I want to tell you how big a molecule is, if I want to tell you that my alkane that I've got here has got 4 carbons, I'm going to call it butane, because there's 4 carbons per molecule. So that is butane. If I tell you that I've got methane here, then you know that it must have 1 carbon per molecule, because I've called it methane. If anyone's not happy with that, let me know. Otherwise, we'll keep squeezing. Monkeys eat perfect bananas. Exactly. Lovely, Edward. Very good. So these ones you do need to know. I think is easier to memorize, but you don't have to memorize. You can definitely work it out. So if I put our general formula, if you can remember, oops, let's go back to blue. If you can remember the alkene general formula as CnH2n+2, which you have to know anyway. So if you can memorize that, you don't have to memorize this table. For lots of people, it is easier just to memorize it though. So let's just have a look. So for 1 carbon, for our methane, we know that it must have 1 carbon, so it's got to be C1. We're lazy though, we don't write the C. H, and we've already worked this out. 2 times 1 plus 2 is 4, so it's CH4. Well done. Or do alkanes ionize better than alkenes, or is that only with acids? So alkanes and alkenes probably won't ionize. I think that's only with acids that you're thinking of. Yeah, we don't really consider alkanes and alkenes to be able to ionize at all, to be honest. It's just the acids. Very good question though. So if you've got 2 carbons, then it'd be C2H, 2 times 2 plus 2. So it would be, well done, C2H6. Very good. Well done, those of you that put that. Fabulous. And then mice eat peanut butter. Mice eat E. So it's our name beginning with E. So ethane, to name that molecule. Just so that we've got some pictures of them as well. So carbon is in group 4. It always has 4 bonds. So that's another reason why we know it's got to be CH4. If there's 2 carbons for our ethane, they join together. And then we've got our 6 hydrogens sitting around the outside. Make sure that every hydrogen has 1 bond and every carbon has 4 bonds. Some of you can read my mind already. You've worked out what do we do if you've got 3 carbon atoms. So it's C3H, 2 times 3 plus 2. 2 times 3 is 6, plus 2 is 8. So C3H8. Mice eat P, peanut butter, P for propane. So P for propane, that one is. And again, if we just draw a really quick picture, 3 carbons are all connected to each other, and then each carbon atom must have 4 bonds. So we fill them all with hydrogens. Each carbon is singly bonded, because we know, because it's an alkane, they must have single bonds. Each hydrogen has 1 bond, so that is our propane. Let's just draw an arrow to those so we can tell which one's which. And then the final one, what's our final one? Well done, teacher. We've got C4. If we've got 4 carbons, that's C4, H, 2 times 4 plus 2. 2 times 4 is 8, plus 2 is 10. So it must be C4H10. C4H10, and that is our butane. Mice eat peanut butter, B. So bute for our naming. And again, all singly bonded carbons, because it's an alkane, so they need to all be singly bonded. And then we fill in all of the gaps so that each of our carbons has 4 bonds. So we fill in all of the gaps with hydrogens. Fabulous. You do need to be able to draw all 4 of these, as I have done on the right, in what we call their displayed formula. You need to be able to name all 4 of these, and you need to be able to give the molecular formula of all 4 of these. So this is why I said some people choose to just memorize the whole table. You can, however, work it out. If you know that an alkane has only got singly bonded carbons, and you know what the general formula is, and you can remember your naming rules, you don't have to memorize any of this. You can work it out. However, it's quite difficult, especially at GCSE, to remember and trust that and then use it in an exam. So I totally understand if people just want to memorize these, or at least get used to them perhaps. So let me know in the chat then how confident you're feeling about the content that we've just gone through. This is a way for me to understand how confident everyone is, but also for you guys to have a think yourselves about how confident you feel with this content. Do you feel like it's very straightforward? In which case you can make a mental note that you found this quite fine. If you're thinking, oh, well, maybe might be okay, perhaps, maybe, yeah, it's probably all right, then give me a 2 or a straight, face, or, oh my gosh, no, that all went over my head. Make a big note to yourself, oh, I'm going to need to go back through this. I'm struggling majorly. Then give me a 3 as well. So it's a way of you guys working out how much you remember and also, or how confident you're feeling, and also gives me an idea of how you're feeling as well. Are you? Fabulous. Lovely. That'll be good. Well done, Deeksha. That's impressive. Chemistry is hard. It's very hard. And unfortunately, it is a big jump up from GCSE. However, most of the content is very, very similar, or especially in the first year, a lot of the content you do is very similar to GCSE. You're just building on it a little bit, which I think is quite nice. It does make it a little bit nicer because you go, oh, we did that at GCSE, didn't we? Which is good, but it is very hard, yes. Okay, let's have a go then at a couple of these questions. We'll see if we can get through all of them, hopefully. But we may need to come back to some questions at the end if we have time. So we'll do this question first. It says, naphtha, which is not a chemical we've heard of, but that's okay, is a fraction obtained from crude oil with the formula C7H16. It says, draw the structural formula of naphtha. Wow, okay, C7H16. Now, I can see, because I know my general formulas, that this is in the formula CnH2n plus 2. So what homologous series does this chemical belong to? What homologous series does naphtha belong to? Oh, well, good luck with those. Well done, Snazzy G, brilliant. And Shreya as well, and Rhea, brilliant, fabulous. Good. It must be an alkane. And Big Man Ting, well done. It must be an alkane. Awesome. Because it's got that general formula, we know it's an alkane. So, because we know it's an alkane, because we know it's got that general formula, we must have all of our carbons must be singly bonded. Must have single bonds between all carbons. So although we've never seen this chemical before, we've got no idea what naphtha is, we don't have to know. This is an application of knowledge question. This is actually a question from the AQA combined foundation paper. So we don't have to know what naphtha is, but we can work it out. We've got all the skills we need to work it out. So it must have single bonds between all carbons, and there's got to be 7 of them. So let's just count. 1, 2, 3, 4, 5, 6, 7. 7 carbons. Each carbon is in group 4. That means it's got 4 outer shell electrons, which means it's going to want to make 4 bonds to get a total of 8. So I must make sure then that each carbon has got 4 bonds to each of those 16 hydrogens. And we can just double check once we've written it in that we have got 16 hydrogens and 7 carbons, in case I've counted wrong. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 hydrogens. 1, 2, 3, 4, 5, 6, 7. 7 carbons. Lovely, well done. So because it says draw the structural formula of naphtha, it doesn't actually want this. It doesn't want that picture. Now, personally, I will always draw the picture first and then write the structural formula, because I find structural formulas harder. And if you are someone who finds structural formulas harder, I would do the same if I were you. So what I'm going to do now is write out the structural formula. Now, a structural formula is different to this drawing that I've done here, because a structural formula should include, it's almost like you're reading it from left to right, you're reading the molecules. So I've got a carbon bonded to 3 hydrogens, a carbon bonded to 2 hydrogens, a carbon bonded to 2 hydrogens, another carbon bonded to 2 hydrogens. How am I on? 4. Another carbon bonded to 2 hydrogens, another carbon bonded to 2 hydrogens. How many have I got now? 1, 2, 3, 4, 5, 6. And then finally, a carbon bonded to 3 hydrogens. Well done, Deeksha. Brilliant. Fantastic. So actually what they've asked for is this bottom one. However, don't panic, because you would get a mark for the displayed formula for the drawing that I've done here. If you did it in the exam, you would get marks for both. So don't panic. If you aren't as confident, you would get marks for both. What do we get the marks for? We get a mark for the single bonds. 1 mark for showing they're all single bonds. One mark for having the correct formula for having the C7H16. So for having the right number of carbons, the right number of hydrogens. And then the final mark is for the full structure. All in a line, all bonded to each other, 3 marks. So if you made a couple of mistakes, perhaps you got the right number of carbons, but you didn't get the right number of hydrogens, you could still pick up some marks here, which is good. Okay, we're going to skip the next. Oh, good question, Edward. Would you get the mark if you draw the structural formula like that? CH3 and then CH2, 5, CH3, yes, you would. Yeah, absolutely. Good question. That's, yeah, so if you drew those 5 as a collected group, so you did CH2 brackets 5, just as you've done there, absolutely perfect. Yes, you would get the mark for that. Good question. Okay, I'm going to skip these next couple of exam questions. Apologies. If you'd like to have a go at them in your own time, please do, but I'm not going to be able to give you the answers. Actually, I can give you the answer for that one, because you can have a go at it and just double check your own knowledge in your own time. But we're running out of time a little bit, so I'm going to need to skip ahead. So, oh, sorry, I didn't actually say. So I won't give you the answer to the previous page, but if you want to have a go, the answer is D for this multiple choice question. So check that you're happy with that. Check that you think that that's correct in your own time. So let's have a look at part 2, properties of alkanes. So our physical properties of alkanes. We spoke a little bit about our physical properties, and we said because alkanes are a homologous series, their physical properties change as you go through the groups. So the physical properties of alkanes depend on their sizes. How big the molecule is. Let's say that in the size of the molecule. Depend on the size in the molecule. So as you go down the homologous series, we go from methane. meth for 1 carbon, methane, to ethane for 2 carbons, to propane for 3 carbons, etc. And it keeps going, methane to ethane to propane to butane, and then on into molecules that we don't need to know at GCSE. What happens to the boiling point? As the size of the molecule gets bigger, do you think there are going to be more or less interactions between our molecules? So with propane, for example, is a bigger molecule than methane. Are there going to be more interactions between propane molecules than there are between methane molecules? If they're bigger, what do we think? So as the size of the molecule increases, do the intermolecular forces, the forces between molecules, are they going to get bigger or are they going to get smaller? What happens, do we think, to the size of the intermolecular, the forces between molecules, intermolecular, oops, can't spell, molecular forces? Are they going to increase or decrease? If we think about it in terms of, if we model it as if you've got lots of people lined up against a fence, and they're all linked by their arms. If you've got lots of them linked up by a fence and they all are linked to each other, but then they kind of hold on to the fence as well, is it going to be easier or harder to pull a long chain of people off or one person? If there's more of a molecule, if the bigger the molecule is, you're going to get more intermolecular forces, bigger, greater, stronger intermolecular forces. So as the size of the molecule increases, the size of the intermolecular forces increase. That means, whoops. Yeah, exactly, Rhea, well done. That means then you have to put more energy in to separate them. Well done, Sen, exactly. You have to put more energy in to separate them. So if you have to put more energy in, perhaps heat energy in to separate them, is the boiling point going to increase or going to decrease? If you have to put more energy in order to separate them, in order to separate the particles, you have to put more energy in. Is the boiling point going to increase or decrease? Anyone know? Yes, well done, Rhea. More energy needed to break bonds. More energy needed to, and I'm just going to change your wording ever so slightly to more energy needed to overcome the intermolecular forces, because they're not bonds between molecules, they're intermolecular forces, but the principle is the same. So more energy needed to overcome intermolecular forces. Very nice, well done. Okay, the main thing you need to take away from this is the boiling point increases as you go down the group. So as you go down the group, like this arrow is doing, as you go down the group, the boiling point increases. Okay, let's, oops, I just pressed the wrong button there. Let's whiz on, because we're slightly running out of time, and I'd like to have a go at doing these exam questions if we can. So an intermolecular force, inter meaning between, molecular, between molecules. So it's an intermolecular force. So between molecules of methane, there will be intermolecular forces. So there are bonds inside methane. And then if I have another CH4, another CH4, another CH4, etc., nearby, there will be what we call intermolecular forces between the molecules. There'll be attractions between the molecules that are what stop it from boiling or allow it to boil, depending on how much energy we've put in. And those are the things that we try to break or overcome when we try to boil something. So an intermolecular forces is the force between molecules. Lovely. Right, let's have a quick look at viscosity and then flammability. So viscosity, this is very similar, and I love using this analogy. Viscosity is how easily something flows. Something like honey or syrup is really viscous because it doesn't flow very easily. Something, so it's very viscous, it's got a high viscosity. If it doesn't flow very easily, it's got a high viscosity. What do you think about the size of molecules? As you go from small molecules to longer molecules, is the viscosity going to increase or decrease? Think about it in terms of rice versus spaghetti. If you're trying to pour rice, does it pour quite easily? Small molecules, does it pour quite easily? Versus if you try to pour spaghetti, can it pour and flow really easily? Or does it all just come out in one lump? And this will help us, hopefully, to think about what happens with our molecules. As the molecules get longer, does the viscosity increase or decrease? What do we reckon? Our trend in viscosity. So viscosity as molecules increase in size. Yeah, exactly right, Rhea. Well done. As molecules increase in size, they oh, my pen's gone funny. Oh dear. They get more viscous. Viscous. No. Can't spell viscous. Viscous. There we go. As in they can't flow very easily. We can't pour them very easily. They just come out as a lump. Is a nice model to think about it. So as molecules increase in size, they get more viscous because they can't flow very easily. And this is because, again, the intermolecular forces increase. And again, we can use the spaghetti analysis and rice. You can pour rice because they don't get very tangled up. If you've got spaghetti, cooked spaghetti, it gets all linked to each other and it gets all connected. And therefore, again, when you try and pour, it's just going to in a big lump because they're all attached to each other. They're interacting with each other. They've got all these intermolecular forces going on. So as you get a bigger size molecule, you get more intermolecular forces. When we talk about viscosity, we're only thinking about liquids, just to put that in there. So methane, which is a gas at room temperature, we're not going to be able to describe its viscosity because it's a gas. Okay, final one. I'm going to need to whiz on, and then unfortunately we're not going to have time to do our exam question. But our flammability, we need to talk about flammability. Now methane, you may or may not know from practical experiments at school, methane, very flammable, very, very flammable. So if methane is really flammable, we can assume that as the molecules get bigger, methane being the smallest alkane, as the molecules get bigger, they get less flammable. And that's absolutely right. So the trend in flammability, so flammability, oops, let's write this in another way. As molecules get bigger, their flammability, your ability to set them on fire, decreases. Substances are easier to ignite, as in easier to set on fire, if they are in the gas state. And as we saw on a previous page, their boiling points increase as they get bigger, so you're less likely to find them in the gas state. So similar thing, as molecules get bigger, their flammability decreases. They're easier to set fire when they're in the gas state, but as your molecules get bigger, they're less likely to be in the gas state, so they're going to be harder for us to set fire. So something like propane, we have propane tanks, which we use propane lots for cooking, heating homes, etc. We use propane because it is still flammable, but it's less flammable than methane. Okie dokie, right, I'm going to need to whiz on. So hopefully everyone's feeling super confident. If you want to have a go at this exam question, just double check that you're happy. The answer's B, but please, oops, the answer's B, but please make sure you're happy with why it's B. Make sure you can discount all the other answers, but I'm not going to be able to go through with that now. So just to finish up, you should now be able to understand the definitions of common terms using organic chemistry, understand what an alkane is, including some examples, and understand the trends in the physical properties of alkanes. If anyone has any questions for me, please feel free to ask, but just don't forget to have a look at our upcoming web classes in case there's something that you fancy coming to. But otherwise, thank you so much for coming, and thank you very much. I will just answer this question. Could you say the increase in viscosity along a homologous series is due to both increase in weak non-bonded transport as well as molecular change? So I think my spaghetti analogy is more because what I'm using to model the intermolecular forces is friction, which is another example of an inter-object force. So I'm kind of mixing my analogies by using it, because friction we talk about when we're considering forces in terms of movement forces, and that's what actually stops spaghetti from being able to move past each other rather than intermolecular forces. So I'm using forces, if that makes sense. So I wouldn't necessarily say it's both of them, but the model uses friction, and it is modeling intermolecular forces, if that makes sense. But very good question. Cool. Okie dokie. Thank you so much for coming, guys. Well done for being so on it. Had some fabulous answers, and some of you have been awesome. So well done for sticking with it. Good luck with your exams. I know that exams are coming up soon. We will continue to have our YouTube classes, and we do have them coming up in, what is it now? May, June, and I believe July as well, but we just haven't got them up on our schedule yet, but they will be coming. So keep an eye out for those. Good luck with all of your exams if you've got any coming, and we'll see you at a future web class. Thank you so much. Well done, guys. Thank you very much. Bye. Bye, guys.